There it is. Welcome to those of you who have joined us already. We'll get started in about 1 minute once folks remember how to register and get into the meeting room. All right, my clock is showing us at about 1 minute past the hour, so I will go ahead and get started so that our speaker has plenty of time to cover all of their slides and information and time for questions afterwards. So welcome everybody to the first LPI virtual seminar of 2023. We're happy to have you here and we're really excited to be welcoming our guest speaker this week, Nick Borsato. Nick is a third-year astronomy PhD student at Lund University in Sweden and also working, I believe, with researchers at Macquarie University in Australia. He specializes in observations of exoplanet atmospheres and focuses on spectroscopic transit observations of ultra-hot Jupiters. So as usual, for the format of these talks, if you have questions, you can type those into the chat box. You can do those throughout the talk and we will read them out loud to the speaker afterward. Or you can save your question until the end and raise your virtual hand and we'll call on you to unmute yourself and ask your question directly. I think that's all we need to cover. So I will turn it over to you now, Nick. Thanks so much for being here.
Thank you, Sam, for having me. And I'd also like to extend my thanks to LPI for letting me give this talk. It's really nice to finally be able to sort of promote the results of my project, which I've been working on for a few years now. So without further ado, I'm going to present to you expanding the limits of chemical searches within ultra-hot Jupiters, with the specific objective of showing you new detections in the atmosphere of the ultra-hot Jupiter that I observed. So to get started, I thought I would give you a little more background context to who I am. So I'm originally from Australia before moving to Sweden to start my PhD. So I did my bachelor's and master's in Australia. And not only am I interested in the research that I do, but I'm also interested in outreach opportunities. So I wanted to sort of take this time to promote the podcast that I'm currently a part of at my university, which we call The Meridian. And pretty much it's a podcast where we interview a lot of astronomers and talk about everything to do with astronomy. So if you guys are looking for a podcast listened while you do your laundry, I think this is an ideal kind of example to do. And basically, I just like to try and distill the knowledge that I have into a digestible format so that other people can understand. Because I think that outreach is a very important skill to have for most science, especially in a growing world where people are becoming more skeptical of what scientists are saying. But more focusing on my science, I do focus on transit observations. And today I'm going to present to you results that I obtained from archival data sets from 2 telescopes. So the first telescope is the TNG, which is in La Palma in the Canary Islands, and which uses the HARP spectrograph, optical spectrograph. And the second is the Calmness spectrograph in the Calo Alto telescope in the south of Spain. So I used these to basically build up the understanding and knowledge that was culminated in my first project, and I'm going to use this as a springboard in my second and third project of my PhD. So that's enough about me. So the question I want to propose to you is, how do we detect chemical species in exoplanet atmospheres? Because if you think about it, it sounds like almost an impossible task, because when we detect exoplanets in transit, we usually look at how the whole planet blocks out the stellar light if we're looking for a transit event. And this, if you're lucky, will block 1% of the light of the star. Now, if you extrapolate this to, for example, Earth's atmosphere, and you were to take a cross-section of the sphere of Earth, the atmosphere that's transparent would take up about 2% of that entire annulus. So you're looking at 2% of 1% of the stellar spectrum. And that's not including also noise or atmospheric effects that can get into your telescope. So the idea is that it's very, very hard to observe any sort of atmosphere around any exoplanet. And there's a reason why we haven't done it, or we hadn't done it for a very long time until probably about 10 years ago. But I'm going to run you through basically the basic concepts on how you would detect chemicals in the atmosphere to detect what kind of constituents are in, and then exactly show you what I built on this idea. So the idea is, if we want to try and see the atmosphere of an exoplanet, we have to sort of come up with a way that we can do that. So let's first observe a transit event, because in a transit event, the light from the star, three things happen to the light from the star when interacting with the planet. So if you look at this sort of picture that I drew, the green lines from the star basically pass by the planet and don't interact with the atmosphere at all. And then when we receive that, we get a stellar spectrum imprinted onto our spectrograph. The second most dominant constituent of light is the light that strikes the surface of the planet. And that gets completely blocked by the planet. And so we see that as the dip in the brightness spectrum of in our light curves. The third light, which takes up the smallest amount, is the light that passes through the upper layers of the atmosphere. So this is where the atmosphere isn't opaque to the photons that are running through it. And during this process, or during this moment, the photons obtain an absorption profile of the atmosphere of whatever planet is passing through. And so some of the light that reaches our telescope has a chemical fingerprint of the atmosphere that we're looking for. The problem is it's all muddled up with a lot of other information. So you have the star, but you also have things like the ISM interfering, and also the atmosphere of Earth interfering as well. So the idea is that if you could feasibly filter out these things and remove them, you should, in theory, have the lines of the atmosphere of an exoplanet. However, that's the idea behind it, but how could we actually possibly come up with an idea to do this? Well, the first thing is you need an ideal target, right? Something that's going to give you the best chance of being successful in whatever scientific result that you want. So what ideal targets we want is, we want a planet with an extended atmosphere. So that's the idea, is that the larger your atmosphere that's transparent, the more absorption that's going to happen. So the more flux is going to be entering your telescope. So that's sort of a no-brainer. And the second one is, we want a simple atmosphere. So what I refer to a simple atmosphere is, instead of maybe for an Earth-like atmosphere, which is composed of molecules, maybe we should attempt to find an atmosphere that is atomic, because when you have a more simple atmosphere, there's less to model. And so then there's less interfering with your inference and conclusions that you're drawing when you finally obtain a result. So we want something that's like that. The third is, then we want efficient absorbers in the optical. And this might seem a little bit nuanced, especially in the age of the JWST now, what we look at looking at infrared. But the reason why we want to look at optical is astronomy is built on optical observations. And so if we're trying out a new technique or attempting to find something that's very difficult, we want to do something or use observations that we're very good at taking. So we try to aim for something that gives us an optical signal. And finally, we want a planet that has a short period. And the reason for that is because we want to be able to observe it multiple times. The longer the period, less chances you're going to see. And so there's less chance you'll be able to follow up and repeat observations. So what type of planet is the best planet? Well, probably the title of my talk gave it away. It's ultra-hot Jupiters. So ultra-hot Jupiters pretty much are Jupiter mass planets that orbit very close to the star. So about 8 times the distant, they're 8 times closer than Mercury's orbit on average. And so at this point, they reach temperatures of about on the order of 2000 Kelvin. For those of you who may not be so have a mental picture of that kind of order of magnitude, M dwarfs, the coolest type of M dwarfs are around 2000 Kelvin. So these have equivalent temperatures regimes to stars, except they just don't produce fusion in their cores. So we have the type of planet that we want. So then it's like, what ultra-hot Jupiter should we observe? So there's about 10. So we classify ultra-hot Jupiters as roughly having a temperature above 2000 Kelvin. But the main definition of an ultra-hot Jupiter is that in the upper layers of its atmosphere are largely atomic. So you have dissociation of molecules because it's too hot. And also another one of the most critical features of these planets is it's so hot that you don't get cloud formation as well. So a cloud deck could create very opaque atmosphere. And so having a transparent atmosphere is crucial for these kinds of observations. So this leads me to my favorite of the ultra-hot Jupiters, and the planet that I am working with is Kelt 9b. So if you think of ultra-hot Jupiters, Kelt 9b is the ultra-hot Jupiter. So it is the hottest known planet currently to exist. It has so much so if you were to create a scatter plot of ultra-hot Jupiters, you need to sort of make a second scatter plot because it sits so far away in its temperature range. It has a temperature of 4000 Kelvin. So this is things really, really hot. And if I play this animation, this is sort of an imagination of what the transit event of Kelt 9 would look like. So it's got 3 Jupiter masses, so it's slightly larger than our Jupiter. And it has a very short period and a very small semi-major axis. So some of the really cool things about Kelt 9 is, one, it has a very simple atmosphere. So it's one of the more easier planets to model. Some modelers think it's a more boring planet to model, but I think if it's easier to observe, it's finer to observe. Its atmosphere is currently eroding. So it has a massive hydrogen tail that follows along from the immense radiation from its sun. And we've actually managed to observe this. Basically what you do is after a transit, if you continue to observe a little longer, you see that actually the light of the star takes a while to go back to its normalized brightness level, and it's because there is a tail following along. I'm not going to talk about that so much, but I think it's a really cool feature of this planet. One of the main things, and one of the things I focus on is I focus on detections of chemical species in the atmospheres of these planets. And the reason why I do this is that, and the reason why chemical species are an important result to start off with, is they tell you what's inside the atmosphere. So a lot of targets actually have been shown to have no detections in specific species like titanium. And it's been argued that because, for example, condensation temperature, you can argue at a condensation temperature that certain elements get rained out into the core of the planet. So you can, if you look for species and you can't detect them, or you can't, that gives you an idea of what kind of atmosphere you're looking at the moment. And then that allows you to add a springboard onto other questions that you could possibly ask later. So there are 10 currently atomic and ionized species that are known to exist in Kelt 9. I won't list them here, they're just put on the slide. So my idea is that, well, how do we find these elements? So the first one is, say we were to take out the star and take out Earth's atmosphere, you should be left with singular lines of the transmission spectrum of the exoplanet. So we actually do find this. It's very possible to see singular lines of a ultra-hot Jupiter using a 4-meter class telescope. So you don't need to use the VLT or Keck or any of the other 10-meter class telescopes that exist. So these 3 results show the resolved lines of hydrogen, calcium, ionized calcium, and ionized iron. And so this happens routinely, and there is a body of researchers that do this quite often. However, this only constitutes 3 of the 10 species that I said were detected. And a lot of species actually don't have singular lines, are too faint for singular lines to be resolved through the noise spectrum. Because you can see here that all these detections are almost completely masked by noise. So what we need is actually a technique that can dig the flux information of every kind of absorbing species that exists in the planet out to sort of provide a detection mechanism. And so to do that, we use something that's called the cross-correlation technique. So the cross-correlation technique effectively is a weighted average of line positions. So the idea is, say that you can't see one singular line, why not combine all the lines in the spectrum into one average line? because effectively what you can do is that will sum against the noise, and you should have a higher contrast. So combining a single peak that sits above the noise. And to do this, it's pretty much you create a weighted average using a spectral template of whatever species that you're looking for. So to create a spectral template, we ask a theorist like, hey, we want you to model a transmission spectrum of Celt9 under this parameter set. They say, sure. And then it's like, okay, but just give us the iron lines instead. So then they go off and they run their simulations and they give us the iron lines that we expect to see. Then we turn these into a set of statistical weights. This weight is then, we then average where we expect to see the lines in the spectrum using these weights, and that should effectively push the signal above the noise floor. One of the issues is, though, during a transit event, the radial velocity of the ultra-hot Jupiter will change. So firstly, it'll come towards you and then move away from you. So you don't actually know where the line positions are on your spectrum in your spectrograph. You could theoretically model where you would expect based on the orbital velocity of the planet, but through propagation of uncertainties, you're never quite sure exactly where it is. So instead, what you can do is you can sample a bunch of different radial velocities for a given timestamp, and at the specific radial velocity of the planet, you get a maximum peak. A maximal peak should occur. So to help, it's a bit difficult to visualize what cross correlation actually does, because there's a lot of words in a very simple equation which doesn't really convey the meaning. So I have created a GIF to sort of give a better understanding of this. So on the top, we have a transmission spectrum from a very short wavelength range. And then we have our template, which is plotted in red. I've simplified the template just for reasons that I'll show a little bit later in my presentation. But the idea is when I play this movie, the average is going to sum and then move across. It's going to take an average and then Doppler shift the template slightly, take another average, Doppler shift again, and you're going to see a cross correlation function forming. In this model, my planet's velocity is at 0 kilometers per second. So at a Doppler velocity of 0, we should get a peak forming. So if I run this, you see the line sliding across the spectrum. And then when it hits 0, we do get a peak forming in the center. You may find that there are this is effectively how we create signals. There's a few other interesting components in this cross correlation function that I've found from looking for other species, which I'm going to go into later. But effectively, we're trying to find a peak in the center, which represents all the ions that are being summed together. So to sort of give you what a standard result in cross correlation analysis is you get these three plots. Usually they're these three plots. Sometimes you get the plot in the middle. Sometimes you get only plot in the middle and on the right. It gives different flavor. It depends on how you prefer, but it's always one variation of these three. So the first plot on the left is the cross correlation function. So that peak that's sort of lined up in the middle happens at a specific radial velocity of the planet. So when we're observing a transit, we don't just take one exposure of a transit event. What we want to do is take multiple exposures over time. And so at that point, the cross correlation peak will shift throughout the transit as the radial velocity changes, which you see here. As time on the time axis from 0 to 40, as we see a radial velocity change, the radial velocity changing of the planet changing until it goes from negative to positive, showing that the planet is passing through its transit. So this is basically, we call this the planetary trace, which shows the path of the planets in radial velocity space. And we then move on to the second plot. So one of the problems about cross correlation is sometimes it's not strong enough to pull out the flux absorption from the transit event itself. So what you want to do is you actually want to stack every exposure you have taken during transit on top of each other to once again boost your signal. So obviously the radial velocity follows the formula is equal to the orbital velocity times the sine of the orbital phase and the inclination. If you're assuming an inclination of perpendicular, it's just the orbital phase. So you can find a way to effectively rotate this trace until it becomes vertical. But once again, we don't know exactly when the orbital trace will become vertical. So what we do is we take an average of each of these we take an average of this array, a vertical average of this array, and we create a row. And so we then shift the pixels slightly, take another vertical average and create a row. And so what happens is you get a rastering of potential averages forming along this plot until you build up, and a peak usually forms at the orbital velocity of the planet, which is the semi-major amplitude, known as often described as KP, against the systemic velocity or the radial velocity of the stellar system now. And so from this, we get our what our signal is. We get a nice bright peak in the center of our plot. We say that we've detected a signal. One thing for some housekeeping, you may notice that we go from a dark spot to a bright spot. The reason for that is just it's standardized. We like seeing bright spots in our papers, so we tend to multiply by -1. So these are absorption features, but they look like emission features just because it's a bit easier for your eye to track. So moving from this, we then take where the peak forms in this plot, where the brightest spot is, and we take where that row is, and this becomes the one-dimensional cross-correlation function. So the idea is it's the idealized summation of all exposures and all flux. So at this point in time, you've effectively combined every potential piece of flux information about your planet that you can. And that's what, so if you can't, there's nothing really much else you can do to really dig out the planet signal at this point in time. So we use this. So in our report, we had 4 archival transits, and I combined them together to reproduce the 10 detections that were already made. So we see here that we get these nice bright features forming. Hydrogen is very bright, and to certain degrees, the quality does change slightly, but all in all, we do get strong detections, and we were able to reproduce the results in literature. So then I was like, great, we can combine these spectrums together. I want to look for something else. I want to look for more species that haven't been detected yet. So I asked myself, it's like, what if we go deeper, and how can we go deeper? And to do this, I had to sort of take a step back because, and think of a more simple case of cross-correlation, because there are some intrinsic properties of the cross-correlation technique that often are overlooked, and that actually is undermining the ability to claim detections or even find detections of elements in the atmospheres of exoplanets. So the idea is just imagine a planet spectrum. So imagine we can take a spectrum of a planet without the star interfering and without any kind of atmosphere, Earth's atmosphere or anything like that, and we can reduce the noise to 0 if we want. And we also set the radial velocity at 0 kilometers for simplicity. I want to ask, what kind of cross-correlation function will form if you do that? So to make it even more simpler, assume your planet only has 3 species in its atmospheres, species A, B, and C, where species A has a lot of lines in the spectrum. So for example, iron has a lot of lines in its in the optical. B has 50 lines, so less, but it still contributes. And then species C only has 5, and we're going to search for species C. So you may think, is there any kind of atomics or species that only have individual lines? And the answer is yes. A good example is strontium, only has about 8 strong lines in the optical. So this is a very real scenario that can happen. Additionally, for more simplicity, let the species have the same line depths. So, because remember that I said that the cross correlation is a weighted average. So if we have every line having the same line depth, then the average should be equal to the length of each line. So we should, in theory, if we do apply cross correlation, get a value of 0.005. So if we know the answer ahead of time, it makes us understand what's going on a little bit more. So what happens when we cross correlate? So now, before we do, we'll add noise into our spectrum. So now we have both a planet spectrum and some Gaussian noise added to the pixels on each one. So I've recreated our standard plots that we're used to. And so this is what happens when we have a signal to noise ratio of 25. So if you have a look at the cross correlation map, all you get is a noise spectrum, which is, okay, not so surprising. If we move the KPV sys plot, you see something interesting. So at the expected planet velocity or system, we do see a small peak forming, but it's dwarfed by this right peak over here. And you want to ask yourself, like, what is that? Because these things appear all the time. And in some results, people think they're tentative detections of some weird atmospheric effects going on. But I'm going to show, remember that we have a velocity of 0 kilometers per second, and I haven't assumed that any kind of atmospheric dynamics are occurring. So there's something else going on here. So then if I increase the SNR, once again, you see that, because you could possibly say maybe it's just a noise peak or a noise artifact. There's just somehow we're going against the grain. We just got unlucky. We've got a peak. Well, so if I increase the signal to noise, the peak still stays the same. Well, it does get a little bit weaker, but it's still present, and it's still the strongest peak in the spectrum. Also, if you're very lucky, you may see that there's actually a streak starting to form on this cross-correlation plot, but there you have to have quite strong eyes. If you go further, once again, we start seeing our signal peak forming, which is nice. And you also can start to see the traces beginning to form as well. So one of the things that you can take away is that the KPV-SIS is actually a way of extracting out a signal, even if you can't see it in your cross-correlation trace. But once again, we do see, not only does this peak form, we see a second peak starting to form on this side as well. So if I increase again and a third time to a very high signal to noise regime, you can see, well, some really interesting features have now formed. In the cross-correlation map, we see the planet's trace forming, but we see also copies of the trace forming here and here and here. Basically, there's this slanted kind of shape that's carrying all the way through. Then if you transform your cross-correlation function into KPV-SIS space on the KPV-SIS map, these slanted structures become these kind of elliptical structures, for lack of a better term, that are placed in the same, with their centers located in the same central locations of each point. So there's something interesting going on. And finally, you've also seen that while we do have now a maximized peak at where we expect the planet's signal to get, we have two secondary peaks that are also quite significant. And we've increased the signal to noise. So if you assume any kind of photon or Gaussian noise, that sort of goes against any kind of logic that you might have, right? You take more measurements, any kind of random noise structures should be beaten down. But in this case, we're making them stronger. So it suggests that there's some kind of systematic structure embedded in the cross-correlation function that hasn't been sort of accounted for. So what you can do is, basically what my supervisor and I came up with is, since we now know that there's only 3 types of species in the atmosphere, we know what the signal should look like, but instead of cross-correlating with the entire spectrum, how about we create a template of species A and species B and cross-correlate species C with both of these templates? What kind of signal would you get from that? Well, you wouldn't expect to see a signal located at the center of the planet spectrum, because there's no line, the lines won't line up at that specific point in time. However, what you will see is artificial peaks forming alongside the spectrum. And the idea is that it's because this is the inefficient summing or averaging of just the spectrum where it is. So there's no noise interfering. So basically what we're doing is you get effectively the lines in the spectrum lining up with other species and taking an average of those lines in an inefficient sense. So if you do that, if I take this plot and cross-correlate with each template, I get something that looks like this. So in blue and marked with the regression model is the signal that we had. And you can actually see that we have in purple, we see our expected signal, but with the cross-correlation function with species C against species A, we see that there is this underlying structure which co-adds with the signal to produce the final peak. And so what this sort of means is that other species will be adding to a cross-correlation function's final result in a systematic way, which could interfere with actually a decline of detections in the atmosphere. Because, for example, say that you think that you see a detection, but what you really see is that your template just correlates quite well with a grouping of lines in your grouping lines of another species and forms a peak where you would expect to see a peak. You may claim a detection that actually isn't there. And additionally in that, if you were to take more follow-up observations, which is commonly what is actually quoted in literature, you would actually statistically prove that your detection is still there. So this is sort of a problem because this systematic uncertainty doesn't go away with more observations. You need to find a way to sort of model it. And so that's what we do. Since we know how to create, we know where aliases come from, you can feasibly construct them by basically asking yourself, what would contribute to the alias structure of a cross-correlation function? And the answer that we've come up with is every element that's been detected in the atmosphere of Kelp 9b could be an alias contributor because it's probably one of the most strongest absorbers there. So it's going to likely contribute to the cross-correlation function. So you can do that. So we basically constructed 10 alias profiles and then ran a linear regression model on our cross-correlation function ourselves. Basically what that means is that we were trying to fit the peaks that were away from the signal, as well as fitting the peak at the signal itself. So it gives you a way to control for these alias structures that are there rather than considering them as random noise, which isn't correct to do, and which is common in this sort of field of research. So with actual data, we got a positive result. So this plot is the cross-correlation signal of neutral magnesium, which you see plotted in teal. Plotted in pink next to it, or magenta, is the ionized iron aliases that we predicted to exist. And you can see, not at the peak, but we get a nice agreement of iron aliases in quite a few different locations. So this was a suggestion. This suggests that actually aliases are present, and we were able to actually detect ionized iron in the atmosphere of Kelp 9b while searching for neutral magnesium. So this is a way to actually detect elements without actually looking for them in the first place. Now, in this plot, we also see non-significant aliases. So the other aliases didn't have a detection threshold above 5 sigma. So the way we would detect we claim for a detection is in our linear regression model, if the coefficient that models each aliases has a significance above 5, greater than 5, or a t-score greater than 5, we claim a detection, which is sort of the standard in this field. So none of these other coefficients had a t-score greater than 5, but they still helped to constrain the overall alias structure underneath. So it's likely that still these aliases do exist, but they're underlying and they're still buried by the noise, which means it gives you a way to constrain the noise profile without seeing the peaks. And so you're not actually fitting peaks for something that you would expect. And so this gives us a better constraint on the detections that we can possibly draw conclusions from. So using this, we were able to find 7 new detections using transit data without using any new data. So the first 2 I will talk about is neutral calcium. So you see neutral calcium uses a pretty light sort of central feature in its KPV-SIS diagram. I will say that my work with aliases probably didn't lead to this detection. It was probably just because people didn't look for it. I just did a bit more of an extensive search. So you could claim a detection using other techniques that this exists. But the second one, vanadium, you see already it doesn't have these nice bright features that the other KPV-SIS diagrams has. It's quite a small feature in an orbital velocity that agrees with some other detections. So you can see that the orbital velocity does vary. So for here, we have a 250 orbital velocity, but here it's at 287. And so you might think, how does the orbital velocity change for a planet that much? And the answer for that is because ultra-hot Jupiters have a lot of atmospheric dynamics occurring in the upper atmosphere. So they have supersonic jets forming around the equator of their planets. And these can be on the order of tens of kilometers per second. So you can get orbital velocity shifts of 20 kilometers per second if the species find themselves in the point in the atmosphere where the velocity is quite large. So the reason why we still claim that this is a detection is because there are other detections that were created by the calmness spectra. So for example, ionized calcium has a similar velocity profile to vanadium. So we're suggesting that these are occurring in the same parts of the atmosphere if we were to consider this to be a detection. So these are the first two detections. Then we also detected chromium and nickel. So you're looking at here, and it's probably like you struggle to convince someone that that's a detection. It looks like a smudge on your plot. And my supervisor didn't believe me when I first showed it to him. And so this is sort of like why we had to develop the theory of alias regression, was because this is difficult to argue that well, it's still pretty apparent that it's there, but it doesn't look as convincing as what we're used to. And so we needed to sort of redevelop our ideas to sort of make sure that what we're doing is grounded in reality. Same goes for nickel. One of the interesting things that you should notice about these plots, which is something that we haven't considered, is that there are a lot of negative facing peaks in these plots, which aren't accounted for in our models and aren't really explained in the literature at the moment. So it suggests that these quote unquote cross-correlation profiles haven't been fully explored in their nature, and there is more that we could use to, more that we can investigate to better understand what we should expect from our results. So these are the two, Nicholas. The last three are probably the most interesting. So we have strontium, ionized strontium, which only recently got detected last year in a transit. I think it was either WASP-76 or WASP-121. I can't remember off the top of my head. But it was predicted to be observable and only recently was observable. Barium-2, if you guys, I'm not sure if any of you are up to date with the literature, but that was a recent detection only a few months ago. It hadn't been detected before. That was detected on the VLT. And finally, we have terbium, which is a very, very heavy element, and also probably the most questionable out of all of the KPV-SIS plots that we see here. This has never been detected in the atmosphere of an exoplanet. So, and I'm also very careful to claim it is a detection. It gives me a 5 sigma detection significance when I run my models, but I have followed it up. And so this sort of needs to warrant more investigation, maybe using different instruments or even like further investigating the structure of the cross-correlation function to fully understand. But I could just say this, it's better to sort of give you a more quantitative understanding of how well these models fit. So in the last part of this, this presentation, I'm just going to run you through effectively how we assess how well these models work. And to do that, we use what's known as a response plot and a residual plot. So for those who may not be so statistically knowledgeable, a response plot basically is if you have a model, it will give you a set of predictions for the data values that you have. If you plot your data values against your data value predictions, you should expect a one-to-one relationship. So you plot a scatter plot, it will follow this trend line perfectly in an ideal world. The same says, if you were to subtract these predictions from the data themselves, you should get a flat line at 0. So basically you see what the residuals are. In the ideal case though, we're dealing with noise, and we also know that we're also dealing with highly systematic structures here. So it's probably not going to be the case. That said, I first, like normal, I sensibly went and had a look at the detections that I've claimed to see how well my models did. So in hydrogen, you see it's almost a one-to-one. And I guess that makes sense because Jupiter mass planets, majority of their atmosphere is hydrogen. So you're getting a lot of flux from there. So we should be getting what we predict, which is great. Interestingly though, magnesium only has a gradient of 0.4 and iron has a gradient of 0.7. So the models themselves aren't perfect fits of the data. And you can see that when I take residuals, there are some kind of subtraction artifacts that aren't accounted for. So this kind of suggests that the predicted model or the predicted signal that we're seeing may not be a good enough replication of what we actually see in our real observations. So this might mean that our templates don't have the right line profiles that we have, and so we can't actually get the subtraction to work. But it sort of suggests that there is more to learn about these kinds of transmission and line profiles and exactly how the cross-correlation function transforms them as well. So we have these. That said, they are still quite strongly positive, and they are also their gradients are quite significant as well. if we look at the new detections, so nickel, chromium, and terbium, I haven't shown all my detections because I don't want to make you fall asleep when we're getting pretty close to the end here. We see that one of the things you probably should notice is that the gradients are not nearly as strong. So this probably suggests a couple of things. We still are working in a noise dominant regime, so we may be able to improve these fits if we were to take stronger data, because we're trying to control for the systematic artifacts. So any kind of alias structures that come, we should know where they will be, and we should be able to constrain them. So it could be just the noise is throwing this off. That said, though, each of these gradients are still greater than zero. You can argue that they're both greater than zero, and they explain some part of the data. So about 20% of the data's variation for chromium is explained by this model. So it shows that the alias regression does show promise. There is still some stuff that we need to work on. And so this is where the issue of terbium comes up, because it has a gradient of 0.089, but its gradient is actually confined. It is considered, like, you can argue that it is greater than zero. So this sort of brings us to, I guess, another point and topic is what actually is a detection, because my model constrains us to a t-score of 5, which is considered to be statistically significant at a very high threshold. But if you're looking at this plot, you probably are a bit skeptical for me to say that this is a detection itself. So if I look at my summarized detections, we see that these are all greater than 5, but it may mean that, and I think what you probably could agree with is when we deal with the cross correlation function and we fit a model to it, and then we apply some kind of bootstrapping method to constrain our statistical significances, we're not dealing with randomized data, which is what these techniques have been built for. We're dealing with highly structured systematic data, which these things do not perform very well in. And so an impending result of that is that you can get more confident results than what you actually should be confident with. So the idea is that if you see detections in atmospheric papers, you should look at the significance number. But if you have a look at this plot here, the ones that we're really sure about have significance above 20 or at least above 10. So even though statistically you should be confident above 5, I would say that you should look for a higher threshold to be very confident. So the idea is that you may want to actually, I don't know if anyone is going to ever attempt a cross correlation in a seminar, but I guess it's a lesson to be learned to sort of show that it is dangerous to sometimes suggest you have a statistically vigorous detection when it actually doesn't really fit the narrative. So that was the final conclusion of my project, is that the systematic effects of cross-correlation functions is somewhat modeling what is a detection and what isn't a detection. So I'm going to summarize, and then we can go around and I'll happily answer any of your questions. So the main thing I want you to take home is when we're searching for chemical species in the atmospheres of exoplanets, the cross-correlation function will have an inherited structure created by other lines that you're not looking for, other lines from species that you aren't looking for. And they're both a blessing and a curse, because we can easily model them. We know where they come from. So that means we can constrain their shapes. So that gives us a way to constrain the cross-correlation signal better. And that has led to 7 new detections happening, and also provide a better statistical context to sort of start off this conversation on what exactly is a detection or not. So we've submitted our paper to Astronomy and Astrophysics, and it's currently under review. So if you're interested, it probably will be published in the next few months. But the next idea from this is to ask ourselves, okay, what happens if we have a lot of data and we really constrain the signal to noise ratio? What then? Can we really show that aliases do exist? And also, what else do we need to model? Like the example, you see these negative troughs that are occurring. Can we find a physical or a systematic reason why they should exist in the cross-correlation function to further control and constrain these detections? So yeah, so that is the end of my talk, and I'll happily take any questions that you have.
Awesome. Thanks so much, Nick. For those of you who wish to express your appreciation, you can either do that by writing something in the chat box or doing your virtual clapping as we typically do. And if you have any questions, please feel free to either write that in the chat box, or you can virtually raise your hand and then I'll ask you to unmute yourself so that you can ask that question. I don't see any yet, so I'll take advantage as my position as host to ask the first question. So it was really interesting to see towards the end there where you were talking about the threshold that you have for I guess the level of significance for each detection, and how to 20 sigma for some of them, which is amazing. Since a lot of geologists work with 1 sigma, that's something that's pretty incredible. But so that, I mean, got me past my initial skepticism of some of the results I saw for like the detection of scandium and vanadium, which when we think of in solar abundances is like a trace element. So like, is there any context for like how much scandium are we talking about in the atmosphere of this hot Jupiter, for example?
Yeah, so that's a good question, and it's basically one of on the forefront of all of our questions that we have. The short answer is we don't know. So they would be trace amounts, but we have found that, like, if you, in planets in our solar system, I do know that they tend to be enhanced in heavier elements than obviously the sun. So we do expect for them to be at a higher abundance, but at the moment, because like you said, like these signals are so faint, it's very difficult to provide any kind of forward model that could predict their abundances. We are trying, but I would say it's still in its infancy. I'd still give it maybe 5 or 10 years before we can give a more concrete answer to that.
Cool. Yeah, I mean, I look forward to learning about that, because I remember reading one of these exoplanet papers a couple of years ago that came out and said something about a scandium atmosphere, and the initial reaction for a geologist is to sort of scoff at that because it's a highly refractory element, so we expect it to, I mean, obviously in an ultra hot Jupiter, it's a completely different ball game there, right? But I mean, to see the level of certainty that you get on identifying these lines is amazing, and I think really highlights the importance of the work that you're doing with these models.
Yeah.
Anyone else have a question? They can raise their hand or type it in the chat box. I'll give just a minute for people to do that.
Thank you, Art. I think one interesting thing about the refractory elements is that we often use their condensation temperatures to predict detections and non-detections. So we can also do this sort of technique on the day side of the planet. So ultra Jupiters are always tidally locked because they're so close. And so often we can see these elements in emission. And so WASP 121 sits on the threshold of titanium's condensation temperature. And so my supervisor basically said that there's been no detections in transit, and he predicted that there would be no detections in the day side, which suggests that it became cold trapped and had condensed into the core of the atmosphere. So we tend to actually use a lot of geological theory to sort of guide us forward in these methods. And it's it's kind of a very interesting time because we are seeing my research network actually hires geologists now to create gas models of molten rock. So it's sort of like, it's this we are related, but now there's this more of a synergy is forming in this sort of field, which is kind of exciting.
Definitely, it's a topic that I think is of increasing interest for a lot of geologists, because we do have the ability to, through experiments and through modeling with the data that we do have, to look at what species of gas are being produced, like when a planet is completely molten. And obviously this is not directly related to something like a hot Jupiter, but as we continue to I guess, develop the ability to look at rocky planets and their atmospheres. It's highly relevant, and so that's a huge, I think, lots of collaborative potential
Yeah.
over the next few years, certainly, at
Yeah.
least. There was another thought that I had. You were mentioning that this, it's the one that we were talking about, Kelt 96, has this tail that gets that's observed actually, and so I wonder, can you also detect these lines in the tail data that you're seeing, or is that not resolvable?
That's a good question. So, yeah, so I would say that it's probably possible. I don't think it's been attempted very much because obviously you're getting, you do run, like the issue is that your abundance drops off. And so then you have less gas that you're seeing through in the tail. So we're only very good at seeing hydrogen at the moment because there's just so much of it.
Right.
But one of the interesting things that you bring up is that we don't actually expect to see ionized species at all in ultra hot Jupiters because it's just they're just too cold to have to continually ionize. And none of our models predict that. So we have to artificially insert some sort of ionization scheme in that doesn't actually have any kind of physical backing. So the idea is that they sit on the top of the atmosphere. So we sort of go ionize, atomic, and then you have your molecular species deeper down. And so it could be a way to detect that you may expect to see more of these escaping from the atmosphere because they're so energetic that they would be coming off quite relevantly. You would need, that might be an interesting proposal idea actually. So yeah,
it would be fascinating from from our perspective, where we're actually not thinking about necessarily observation, but from the modeling perspective, thinking about the fractionation that you would experience, compositional fractionation from the atmosphere getting eroded away is obviously not something, well, thankfully not something that we observe directly here in our solar system. So that would be an incredible opportunity to really see what that looks like in these exoplanetary systems. So that's cool. Let's think more about that.
And I think with like James Webb, this is gonna this sort of a photo evaporative loss for exoplanets is gonna come like much more clearer. It's like it just sits on the cusp of like it sort of perfectly fits into James Webb's sort of profile. So I think we'll definitely learn that. So I'm very excited about what he can do as well.
Are the techniques that you're using applicable at all to the mid infrared or the infrared region, I guess, that James Webb uses, or is that translatable?
So the cross correlation, it's funny, I know I said that we use optical because it's easier, but the cross correlation function was used on an infrared spectrograph before it was used on the optical. It's definitely it's actually probably it's very useful to use because if we have a high resolution, or in high resolution anyway, low resolution, it's a bit different, but with high res, you can see through the Earth's atmospheric lines because they stay stationary while the planet's lines will move slightly. And so they don't get blocked. They actually move out of these offsets. And so you can then use the cross correlation function if you can remove the Earth's atmosphere well enough. And it gives a way to see molecules in the atmosphere of these planets. With James Webb, well, you don't have the Earth's atmosphere to worry about, so that's always nice. But you don't need cross correlation for low resolution because the lines are effectively already summed together. So you're getting so much flux already from the planet system that there's not a whole lot cross correlation will do to boost your understanding. You can just effectively create a forward model and fit what you see instead, and that will give you pretty much the same results as a cross correlation function would as well.
Okay, cool.
Yeah,
and I guess that would be the same for this proposed new giant optical telescope that's sort of akin to the structure, I guess, of James Webb. It would be the same, I guess.
Yeah. Pretty much, it would be to operate on that. Is that for a space telescope or the?
Yeah,
So,
I mean, it's like just was announced like a couple of days ago. So we're on the cutting edge of announcements in
yeah,
this seminar, everyone. So
yeah, yeah,
we're all
yeah, yeah.
fortunate to be here. Yeah, it was just announced. I think it was NASA proposing that there's a multi-billion-dollar optical telescope that they want to do. That's basically the same thing as James Webb, just optical. If
Wow.
anybody
Okay.
knows more about that, they
Yeah.
can feel free to chime in. But I guess I want to give anybody a chance to ask a question. Otherwise, go on. Don't be shy. Well, okay, if anyone does have a question, they can contact Nick via email or anything. Just want to say one more time, thanks so much for being here. This has been absolutely a fascinating talk, and love to have you back again sometime. So let's express gratitude one more time. See them in the chat as well.
Yeah.
And
Thanks, guys.
thanks for being here, everybody. Thanks once again, Nick. And we'll see you all at the next seminar.
Okay. Thank you so much for having me as well. This has been great.
Absolutely, anytime. All right, everyone. We'll see you on the next one. Goodbye.
Right.